Hello, everyone. Welcome back to the second talk of the day. Uh, Yesterday in Fahad's talk, he described the central problem in this line of research, and he gave a very rough outline of the proofs. And today, we're looking forward, Fahad, to a more in-depth view at the proof techniques that you use to obtain these results. So whenever you're ready, over to you.
Okay, thank you. Okay, so we will continue with the topic, which is deletion and elimination to some specific graph classes. Okay, as I mentioned yesterday, this is based on these two papers. Okay, and in the yesterday we defined this elimination distance and then talked about an algorithmic problem, and we stopped in the midway. Today, we will recall some of these things so that you will all be in sync with what we are doing. And before that, I will give you a bit more intuition or like a bit more motivation towards elimination distance. Okay, and then we will move on. Okay, so just pick a candidate, a well-known candidate vertex deletion problem, which is vertex cover. There's a lot of study on that. So you want to find a vertex cover of certain size. Okay, that's a problem. Or after deleting a small set of vertices, you want the graph to be edgeless. Okay. And for this problem, there are a lot of Fpt algorithms known, and a simple branching algorithm will give you an algorithm with running time order 2 to the L into n. You branch on the edges. Okay, this is the algorithm. Okay, now, and this algorithm will also output a vertex cover of size at most L if there is one. Okay, now suppose you have a graph whose vertex cover size is large. Okay, and if you want to find out a vertex cover, then you need to run an algorithm, or like the running time of this algorithm will be 2 to the power your vertex cover number times n. Okay, and when the vertex cover number is large, and this algorithm will be slow. Okay, so then what you can do is you can try for a parameter which is much smaller than vertex cover and try to find vertex cover parameterized by that. Okay, so for example, like this is what I asked. So can we get smaller parameter for finding vertex cover, like which is smaller than the vertex cover? Okay, and then design an Fpt algorithm with that parameter. Okay, turns out that there are a lot of them. Say for example, tree width, path width, tree depth, all these width parameters or these structural parameters are less than the vertex cover number. Okay, and in fact, tree width is less than or equal to path width, and which is less than or equal to tree depth, which is less than or equal to the vertex cover number of a graph. Okay, and a simple or a standard dynamic programming algorithm will give you an algorithm for finding vertex cover in time 2 to the tree width to the n. So if your vertex cover number is much larger, but your tree width is small, then still you will be able to find out a vertex cover. So, and if we are going to if we want to find out vertex cover parameterized by these kinds of parameters, then it is also very well to ask about how to finding out these parameters. Say for example, like that is also an interesting open question, right? Okay, and the elimination distance, which I also mentioned yesterday, which is a generalization of tree depth. So in this talk, like we will be more like interested in tree depth, and the elimination distance will be a generalization of this one. So think about these three problems: vertex cover parameterized by vertex cover number, vertex cover parameterized by tree depth, and tree depth parameterized by tree depth. Okay, so these are the three problems we get, by looking at this deletion version of the problem. Now I will define tree depth formally in the next slide. Okay, we have seen it in the we have seen it yesterday as well. So I will give you first a recursive definition. The recursive definition of tree depth is as follows, right? So if the graph is empty, then there is no vertex, then it is 0. If it is connected, then it is 1 plus minimum of the tree depth of G minus V, where V is a vertex, and the minimum over V. And if G is not connected, it is the tree depth of the maximum tree depth of a component of G. Okay. And so this is a recursive definition, and this also leads to an alternative definition. The alternative definition is as follows. Okay, tree depth of G is the height of a smallest rooted forest F with the following property. Okay, so there is a rooted forest. Okay, and this rooted forest will have n nodes, which is same as the number of nodes in G, and there will be a bijection between V of G and V of F. Think that you are going to place each vertex of G to nodes in this forest F, and there is some constraint. The constraint is for any edge UV in E of G, their corresponding vertices in this forest, which is G of U and G of V, they are in an ancestor, like one is the ancestor of other. Okay, so it should not be like crossing. It should not be like, it should not be, this is not allowed. Okay, so then we say that, okay, so this is what the definition of tree depth. Okay, now as I mentioned, elimination distance is a generalization of tree depth. Okay, now we will define elimination distance to a graph class H, a class of graphs H. Okay, so how do we define it recursively? It is exactly the same way like as tree depth, but here in the first case you will have 0 if G belonging to H. Okay, otherwise it is the same way, like 1 plus minimum over the elimination distance of G minus V if G is connected, where the minimum is over V, otherwise the maximum among the components. Okay, if G is not connected. Okay, and I mentioned that this is introduced by Boolean and Dower in 2016, and again similar to the alternative definition of tree depth, we can get an alternative definition of a for elimination distance to H. So it will be minimum depth or minimum height of a rooted forest, and this time the rooted forest, there will be a bijection from a subset of vertices of G, I will call it X, to the nodes of the forest. And look at the graph G minus X, and that G minus X should belongs to the graph class H. And for any connected component in G minus X, the neighbors of that component in G should belongs to a leaf to root path. Okay, so that is mentioned in this yellow part. And if you take any two vertices in an edge whose both the endpoints are in X, then the corresponding vertices in the forest should be like in an ancestor descendant relationship. So this is the definition of elimination distance to H. Okay, so this is an the top is called the elimination forest, and the elimination distance is the height or depth of this forest. Okay, so any question? Okay, fine. Okay, So this is the definition of elimination distance. Okay. Now, elimination distance is same as tree depth when H contain only one graph, which is empty graph. Okay. So in the bottom, you don't have anything. Okay. No vertex at all. Okay. And another thing you can notice is the elimination distance of a graph is at most the size of a minimum deletion set. What do I mean by deletion set? After deleting, mod number of vertices, you will be able to get into the graph class H. So how you can see, take this modulator and keep it in a path. Okay, and the remaining, so this is modulator and G minus M belonging to H. So this will be an elimination forest. So there will be some other forest which could be much smaller than this one. So this parameter, which is elimination distance, is less than or equal to modulator. By modulator, I mean the deletion set. Okay, so similar to tree depth and vertex cover number. Here I have elimination distance and modulator. Okay. Okay. So there are two questions that of interest, analogous to the case of vertex cover. So what finding vertex cover and finding tree depth. Okay. And similar to that, there are two questions, right? So given a graph G and an integer K, can we delete at most K vertices to get into this graph class H? Or is the elimination distance at most K? That is the second question. The first problem is called vertex deletion to H. Second problem is called elimination distance to H. So we can ask, these questions on various parameters. Okay. The parameters is, the first one is elimination distance to H parameterized by the elimination distance, analogous to tree depth parameterized by tree depth. And the other thing is vertex deletion to H parameterized by the modulator size, which is same as, which is analogous to vertex cover parameterized by the vertex cover number. Okay. Or the solution size. And the third one is vertex deletion to H parameterized by the elimination distance. And this is analogous to vertex cover parameterized by tree depth. Okay. So these three questions are of interest. And so now we can, when you, substitute different graph families for H, you will get to different problems. And this generalizes many problems. Say, for example, this generalizes vertex cover, triangle hitting set, deletion to min degree graphs, say feedback vertex set, lot of problems you can, encode in this one. Okay. Now, first we will consider, like yesterday we considered this one, F-free graphs. What is F-free graphs? So a graph G belonging to is an F-free graph if G does not contain an induced subgraph which is isomorphic to a graph in F, and F is a finite set. So we can call it finite forbidden induced subgraph. Okay. And in the case of vertex cover, F contain only one graph, which is K2. Okay. And so we can ask these three questions, like when H is an F-free graph, for example. Okay. So we'll consider that first. Okay. So now take the simplest version of the problem in that, which is vertex deletion to F-free graphs parameterized by the solution size, which is the modulator. Okay. So can we delete at most K vertices to get into this graph class, F-free graphs, and the parameter here is this K. Okay. And here, like similar to the symbol branching algorithm for vertex cover, we can design a symbol branching algorithm for it. Like you just pick an induced subgraph H of G, which is isomorphic to F. This will have constant size, and hence you can find it. And you know that one of the vertices should be in the solution, and so you branch on. So you will get a recursion tree or branching tree with total number of nodes is d to the power k plus 1, and in each node you are going to spend polynomial time. That leads to an algorithm of this running time. Okay, that is the simpler one, which is analogous to vertex cover parameterized by the solution size. Okay. Now ask our favorite question, which is elimination distance to F-free graphs parameterized by elimination distance. This is the question analogous to tree depth parameterized by tree depth. Okay, so given a graph G and K, an integer K, we want to check whether elimination distance is at most K, or we want to output such a decomposition. So just stick to this decision version of the problem. Okay. Now here this K, notice that what we want an elimination forest. Elimination forest may contain lots of vertices, but we want to check whether the height of the elimination forest or the depth of the elimination forest is at most K. The bounded thing is the depth of the elimination forest. And there is no guarantee on the number of vertices in the elimination forest. It could be large. Okay. So that is one of the obstacles to design a branching algorithm, or like to that matter, like to design any algorithm, we see that this elimination forest is too large. Okay. Okay. Now just analyze. Suppose you have only like every elimination forest is very large. Okay, then what will happen is you can find a small separator which separates lots of vertices, which means that in the middle you can find a leaf to root path, and that will separate the left hand side from the right hand side, and you will see lots of vertices from the left hand side and lots of vertices from the right hand side. Yesterday I mentioned that, and we will invoke a result which says that if your problem satisfies some conditions, and then if you're able to solve the problem on graphs which does not contain this kind of separator, which is like small vertices separating lots of vertices, then that theorem or that result is going to give us an algorithm for the problem on general graphs. So the theorem will restrict, it tells that okay, if your problem satisfies some certain conditions and you are able to come up with a good algorithm on some special kinds of graphs, which is like that does not have these kinds of separation, which automatically implies that your elimination forest cannot contain lots of vertices. So that is a very good thing. And using that structure, if you're able to come up with an algorithm for your problem, then that result will tell us that in fact there is an algorithm for your problem on general graphs. Okay, so more formally we will define SC unbreakable graph. What is an SC unbreakable graph? It's a graph which does not contain a separator of the following form. Okay, so no separator of the following form. Okay, so a separator of size at most C, that is separating the left hand side from the right hand side, where left hand side contains strictly more than S vertices and right hand side contains strictly more than S vertices. And the result I was referring to tells the following: if your problem can be expressed in a logical fragment called counting monadic second order logic, and for any C there is an S, this S is provided by this theorem or this result. If you're able to come up with an algorithm for testing whether H satisfy this property, whether you are able to, if I'm able to come up with an algorithm for testing whether H satisfy that graph property on SC unbreakable graph, not on all graphs. Okay, here D is a constant which is independent of C, S, and the length of the formula phi, and the constant hidden in the big O notation can depend on the size of the formula C as well as yes. Okay. Then there is an algorithm of similar running time for testing whether G satisfies that property psi on general graphs. Okay. So the implication of this theorem is the following. If we prove that our problem, which is elimination distance to F-free graphs, is CMSO expressible, and elimination distance to F-free graph is Fpt on k comma alpha k unbreakable graphs for all k, then elimination distance to F-free graphs is Fpt parameterized by k on general graphs. Okay, so to get an Fpt algorithm for our problem on general graph, we need to prove these conditions A and B. Okay, now yesterday we went on and saying that indeed the condition A holds. Okay, to prove the condition A holds, I said that we can, this problem, elimination distance to F-free graphs, this problem can be characterized by, this problem has a different characterization that will allow us to say that this is CMSO expressible. So I will write down that, I will note down or recall that characterization here, which is elimination distance of G, elimination distance to F-free graphs is at most k if and only if the following hold. There exists a vertex subset X such that G minus X is F-free graph, okay, and torso of X is F prime minor free. What is torso of X? Torso of X is like this is X. It is a vertex, it is a graph on the vertex set X, and you have an edge between two vertices in this graph. If in your graph G, there is a path from these two vertices where the internal vertices are outside X, and that graph is called a torso of X. And torso of X can be expressed in monadic second order logic, and F minor, like test, this property F prime minor free, this can also be written in monadic second order logic, and F free, this can also be written in monadic second order logic, and hence you can write a formula in monadic second order logic for testing whether elimination distance of G is at most k or not. Here I want to point out that this F prime will depend on k, okay, and hence for every k you will have different formulas. Okay, so your problem is expressible in CMSO. This implies that the first condition is done. Okay, now what we need is, and that is yet to prove, is elimination distance to F-free graph is Fpt on these special kinds of graphs, which is k alpha k unbreakable graphs. Once we prove that, we are done. Okay, so now what I'm going to do is I'm going to give you a proof for this. Okay, the second one, and it will be in detail. Okay, so we want to design an algorithm for elimination distance to F-free graphs on this, like we assume that our input graph is k alpha k unbreakable. Okay, now suppose my input is a yes instance, okay, which means that the elimination distance is at most k. Now look at a hypothetical solution which look like there is an elimination forest of depth or height, or depth at most k, and you will have lots of connected component after deleting this X, and each connected component is going to see only from a leaf to root path, and all other edges will also be from leaf to root path kind of thing. Okay, so this is what we know if this is a yes instance. And since the graph, the input graph G is K alpha K unbreakable, immediately we get that the cardinality of X is bounded, or the number of vertices in this elimination tree is bounded. Suppose it is more than this number 2 alpha K plus K, then somewhere in the middle you can take a leaf to root path that will separate the left side from the right side vertices, and there will be more than alpha K vertices in the left and more than alpha K vertices in the right. Okay, so that will contradict our assumption that G is K alpha K unbreakable graph. Okay. And so that is the first implication. So this, the size of the tree is at most X. This is at most bounded by a function of K. And now if you look at the job these vertices which I'm going to play, which will be in these tree nodes do, this will be used to maybe kill an induced subgraph in G which is isomorphic to a graph in F. So it may be used to hit on those, okay, or kill on those structures, or it may be doing a job to disconnect many graphs, right? To disconnect graphs. So one of these two jobs it will be doing. So it may not be doing this alone, it may be doing it with the help of other vertices, but every vertex will have a role which will be towards one of these, right? Either killing an obstruction or to make more connected components so that the depth of the tree won't grow. So these are the things each of these vertices in X is going to do. Okay. Now what we are going to do is we are going to design a branching algorithm for our problem. Okay. So the immediate thing you can branch on is what? Like, okay, before going to like explaining how to branch on, first let me tell you that look at this X, look at this elimination forest. This elimination forest has bounded size. I mean, the size of it is bounded by 2 times alpha K plus K. Okay. And then I can guess the structure of this forest. Okay. Like how this look like. Okay. So I don't know which vertex from G will be a root vertex or the first neighbor of the root. This I don't know, but structure I can guess. Okay, that is an f of k guess. Okay. Now after guessing that, what I will do is I will check whether my graph G has an obstruction, which means that an induced subgraph which is isomorphic to a graph in F. Okay. If no, then we are done, right? The graph G itself is, is F-free. So if we find such a, like we can find if there exists some obstruction, then what we know is at least one vertex from that subgraph, induced subgraph, should belongs to X, should be part of this forest. Okay. So what I can do is what I can guess or I can branch on that vertices, and these vertices may be placed in one of these locations in this tree. Okay. And I can branch on the positions of that tree. Okay. So maybe like the vertex V could be in the position like the third neighbor of the root. Okay. So I can branch on them. So because the number of positions in the tree is bounded by a function of K, and the number of vertices in the obstruction is a constant. Okay. So you just branch on them where it goes to. Okay. So what you do is after, you keep finding out obstructions after, some vertices you will fix on the tree and look at the graph, which is, G minus the vertices fixed on the tree. And if there is a, obstruction, which is an induced subgraph, which is isomorphic to a graph in F, then then you know that one of the vertices should go into X or going into the elimination forest, and the positions are bounded, so you branch on them. After doing all these, we will have, like, after exhaustively doing this branching, like what we will have is like this elimination tree. This is partially filled. The partially filled locations are marked red, and other locations are not. The locations which are not marked red are vacant. That is expecting some vertices from G minus these filled vertices. Okay. Now what I know is in G minus these red vertices, there is no obstruction. That is actually F-free. This I know. Okay. Because if there is an obstruction, I will branch. Okay. So in G minus the red vertices, red filled vertices, that is actually F-free. But it may not satisfy the property we want, which is like any connected component from the bottom can only have neighbors from a leaf to root path. That property may not be met. Okay. So suppose there is a component which see two neighbors in this forest, two filled neighbors. Okay. And they are not in the ancestor, not in an ancestor descendant relationship. Okay. Then look at a path from those two vertices through that connected component, which is marked below. Okay. I know that, in my solution, at least one vertex from this path should go into the top. Okay. Go into the elimination forest. Okay. Because otherwise we will not satisfy the required condition for elimination forest. Okay. Okay. So now I claim that, now look at this path. Okay. Look at this, the internal vertices of this path, and the first alpha k vertices and last alpha k vertices. I claim that one of these vertices from A union B should be in the solution, like it should be in this elimination forest. And can someone say why it is? If it is not, then I say that the graph we started with will not be K alpha K unbreakable. Okay. Now, why it is? Suppose none of these vertices in A or B is not in the solution. Okay, not in the elimination forest, which means that after I deleting my elimination forest, I will have a connected component. That connected component will I will have lots of connected component, where one connected component will contain these vertices and one connected component will contain these vertices. Now, if I take this set of vertices, this set of vertices will separate A from B. Okay, this connected component from this connected component. And that tells that there is a separation which separates, A from B, and both A and B are of size at least alpha K, or like, I will put +1 here. Okay. Okay. And the separator size is at most K. That will contradict, our assumption that my input graph is K alpha K unbreakable. Okay. So, so what you do is, if you see a connected component which is going to have neighbors which are not in ancestor descendant relationship, then 2 alpha K vertices to branch on, so you branch on. So after you do all these branching, what is the property satisfied? Every connected component in the bottom, which will be F-free, and they are going to see only from one leaf to root path, the neighbors in one leaf to root path, and that completes an Fpt algorithm for this problem. Any questions?
Yes. So if I understand correctly, abstractly, are you showing the following problem FPT in K alpha K unbreakable graphs, that given a graph G and let's say a forest on K vertices, whether it is an elimination forest?
Correct. So you forest is given and you need to map vertices from G to this forest.
So, but what is the complexity of the problem in general graphs? So given a graph G and a forest on K vertices, the question is it, and you are also given this capital F, then is this forest an elimination forest for F?
So this algorithm will not give that because we are branching on the number of positions in the forest also, because we want the number of positions to be bounded. If the number of positions is bounded, then yes. Or the number of vertices in the forest is bounded, then yes.
Yeah. Number of vertices in the I'm saying you are given a graph G and a forest on K vertices.
Yeah.
Okay.
Forest on forest with depth K, and number of vertices in the forest will be some function of K bounded by.
Yeah. I mean, K, by K, I mean really F of K, whatever. Right?
Okay. Yeah. And
so,
then you are going to get an FPT algorithm by branching.
But not in general graphs. You are still also using.
Okay, correct. Not in general graph, but in K alpha K unbreakable.
Right. But what is known about that problem in general graphs?
I don't know actually.
So Fahad,
I think you can apply the previous theorem, the Lobsnow et al., and get FPT, what you are asking. So you are asking an elimination forest of a specific kind, right?
Yeah.
So that this algorithm won't give you, right? And I think you could apply the Lobsnow et al. Theorem and prove that it is CMSO and prove only on K alpha K unbreakable graphs, and then probably get it. Because this is bounded size, you are talking about the tree. So you have an additional condition that, torso of X is at most, tree, is F prime minor free, and there is a tree embedding of for X with some certain properties.
Okay. So essentially that's what you have shown. So you're essentially saying in any graph, if you're given a K-sized forest and you want to know whether it is an elimination forest for an FV class F, then it is FPT, because you just apply that black box of unbreakable and then do what you just did now, doing this mapping.
You need to prove this condition A and B, where A is CMSO, that you can prove because that is tree is bounded size, and B you do as I explained here. Because this condition hold. Okay, and there will be a bit of catch, I think there is a bit of problem there, because the tree size is depending on this alpha K, which that theorem is going to say. So probably I really don't know. So that might be a problem.
No, but tree size is a function of K only, right?
No, but this alpha K is provided by that result.
True.
And if you have if you are yeah, correct. No, you can apply. You're right. Because we are asking about the connected component size in the bottom. Yes, you can apply that. Okay, then I will. So we proved the condition A as well as condition B, like these two conditions we proved. And this gives elimination distance to F free graphs is Fpt, and parameterized by K here is elimination distance. Okay, that is what we did. Okay. So what we got is like elimination distance to F free graphs parameterized by elimination distance is Fpt. So it's similar to tree depth parameterized by tree depth. Okay, and the other we already so which is a simple branching algorithm. Okay. Now there is a third question, which is vertex deletion to F free graphs parameterized by elimination distance. Okay, like vertex cover parameterized by tree depth. Okay, we'll answer this at the end. Okay, I will not give an algorithm, but I will answer this at the very end. Okay. Now let's move on to another class. Suppose EH is F topological minor free graphs. Okay. Now I will define, F topological minor free graphs without, going through these minor definitions. Okay. So in the F free graphs, what we want, suppose H is a graph in F. We don't want this graph H as an induced subgraph in my graph. So G is an F free graph if, say, then like suppose H is the only graph in F, then we don't want this H is an induced subgraph in F. Okay. And now suppose I ask about F topological minor free graphs for F containing only one graph, which is this H. Okay. Then the meaning of it is you take all infinitely many graphs which are subdivisions of this H. So one example of a subdivision of H is shown here, which means that on an edge, you are allowed to put many vertices, okay, like this, subdivide edge, okay. You may not subdivide all the edges, you may not subdivide edge at all, but like that will give you infinite number of graphs, okay, a subdivisions of edge. So you may be subdividing once, twice, thrice, million times, okay. So that will give an infinite family of graphs, okay. And a graph G is F topological minor free if any of these subdivision of H should not be present in G as a subgraph. Okay, so that is an alternate definition rather than going through minor or that definition. So look at the subdivisions of H. So there will be infinitely many such graphs. And these patterns should not occur in my graph G as a subgraph. Then I say that G is F topological minor free. Okay. So now automatically, like the problem is like these patterns are infinite in number and infinite in size. Okay. So we can't simply branch on them. Okay. Again, we can ask these three important questions. Vertex deletion to F topological minor free graphs parameterized by the modulator size, and elimination distance to F topological minor free graphs parameterized by elimination distance, and vertex deletion parameterized by elimination distance. And for the first problem, there is an Fpt algorithm which is very recent, and there is no simple algorithm like what we have seen for the previous case. And this is a very complicated algorithm. Okay. So to adapt that is very difficult thing. So what we are going to do is we want to solve the second problem, elimination distance to F topological minor free graphs. We are going to use the first algorithm as a black box. We are not going to adapt anything. We just going to use black box, this algorithm as a black box, and then going to solve elimination distance to elimination distance parameterized by elimination distance. Okay, so that is the plan. But still, it is also a branching algorithm. At the bottom of the branching, we are going to apply Fomin et al.'s algorithm for deletion version of the problem parameterized by deletion set. Okay. Now again, the pattern is same. like what we did for F-free graphs. The pattern is like apply option of it all. Okay. So what we need, we want to prove that my problem is CMSO expressible, and there is an algorithm for the problem on K alpha K unbreakable graphs for all K, and where K is the elimination distance. Okay. And if I prove A and B, then by this theorem or by this result, we are going to get that our problem is Fpt on general graphs parameterized by elimination distance. Okay. So the pattern is same. So now elimination distance to F topological minor free graphs, we can say, we can prove that it is CMSO expressible. So for that, we come up with a characterization when it was F-free. Similar kind of characterization we can come up with for this problem. And it says that if the elimination distance is at most K, elimination distance is at most K if and only if it's both the direction. If there exists a vertex, if and only if there exists a vertex subset X such that the first property, this property is same, and G minus X is topological minor free. That's the only thing. So, as I mentioned, F prime will depend on K. Depends on K. And so, and these characterizations can be expressed in this particular logic. And because of that, you know, A is done. Now we need to prove B. Okay. So again, come back to this case. In the case, come back to this particular case. Okay, K alpha K unbreakable graphs. But here we want to get into F topological minor free graphs. Okay. Now, again, by the same argument, the cardinality of the number of vertices in this tree is bounded by a function of K. Okay, that goes the same kind of argument. And then suppose this is a hypothetical solution and it looks like this, then I claim that there is only one large connected component in G minus X. Suppose there are two large connected components. Suppose this was also large. Then what will happen is this yellow thing. Okay, this path is going to, this path or this separator is going to separate this yellow from that purple. Okay, and both the yellow and the purple are large, which will contradict, you know, unbreakability. So, which means that, you know, there can't be two large connected components. Now, can there be no large connected component? That is also not possible. If there are lots of, like I assume that the graph contains lots of vertices and X is bounded size, and if all the connected component in G minus X is, you know, has small size, like which is less than alpha K, then somewhere one of the leaf to root path will be a separator contradicting the fact that my input graph is K alpha K unbreakable, because many of these connected components I can push to the left and many of them to the right by taking an appropriate leaf to root path as a separator. Okay, so this tells me that there is a unique component in G minus X where X and this tree is a hypothetical solution. Then there is a unique component in G minus X which contain more than alpha K vertices, and the remaining will be all small components. Okay. Now what we are going to do is we are going to design a branching algorithm where we are going to, like, first, what, as we did before, we will guess the structure of the tree. After guessing the structure of the tree, what we are going to do is we will come up with a branching rule, and that will place the vertices from the large connected component to this particular root to leaf path. So I guess the structure of the tree, and this particular leaf to root path, which is TR, where this unique component is going to see. Like unique component is going to see to have neighbors from this path only. Okay, that path also I guess. Okay, which is that path. Okay, so then what we are going to do is we design a branching rule, and that branching rule is going to find out vertices, and that will be placed in this particular path. Okay, and at the end we are going to solve the deletion version of the problem and some more trivial branching. Okay, so that is the high level overview of what is going to do. Okay, now I'm going to explain it in detail. Okay, so as I mentioned, we are going to guess the structure of the tree and which path is this special path where in my hypothetical solution the unique component is going to see have neighbors. Okay, now to design a branching rule, I want to talk about something called alpha k connected set. Okay, an alpha k connected set in a graph D is a connected vertex subset B. What do I mean by connected vertex subset? The graph induced on B is connected. So here it will be D of B connected. That is the meaning. Such that the following hold: the cardinality of B is at most alpha k, and the neighborhood of B is at most k. So it will be like in a graph, a small vertices, small set of vertices, and if I look into the neighbors, this is also small. This may be large. So this is what this B is called connected set. Okay. So pictorially, it looks like this. Okay. Now, and we say that, okay, this connected set is maximal if there is no other alpha k connected set B prime, which is a superset of B. Okay, then we say that it is a maximal, connected set, maximal alpha k connected set. Okay. Now, there is a result which says that the number of alpha k connected sets in a graph is at most 2 to the times this quantity times n. Okay, so this is actually linear in n and Fpt, number of them, and it can be enumerated efficiently. Okay, so this is now. Okay, now what I'm going to do, branching is simple. Okay, so initially what we have, we guess the structure of the tree or the forest, and we also guessed this special path T to R, and G is at the bottom. Currently G is at the bottom because we didn't place any vertex from G to this path or this forest. Okay, so enumerate all the maximal alpha k connected sets, and if one of them, pick any one of them and then check whether that is F topological minor free. Okay, so that we can check easily. Okay, because there are algorithms to test that. Okay, so pick a maximal. So enumerate all the maximal alpha k connected set and check whether there exists one such that the graph induced on the neighborhood of B, which has bounded size. How much size? Alpha k in B, and its neighbors will be k. Okay, so in this graph, so the graph induced on neighborhood of B, it will have size alpha k plus k, and if it is not topological minor free, then what we can say, at least one vertex from this should be going to the elimination forest. Correct? Okay, so you take any alpha k connected set B. Okay, not even maximal. Okay, then if it is not F topological minor free, then at least one vertex from that close neighborhood of B should go into the forest part. Okay. And because of the maximality, we can prove that there is one vertex that should be placed in this special T2 root path, and that can be proved using maximality. Okay, so I will not explain in detail, but you use maximality to prove that. Okay, so what do? You branch on them. You branch on B union N of B and the positions of T2 R path. Okay, so you keep doing this, and at some point it looks like this, right? So you keep doing it, and what is the second time how you do? You look at there will be only one, at any point in time, there will be only one large connected component, and you try to enumerate all let that be D. You try to enumerate all the maximal alpha k connected sets in D, and if one of them is not F topological minor free, you try to branch. Okay, keep doing that. Okay, that's what you do. Like that you are going to do on that unique, like there will be a unique connected set at any point in time that is going to have this property. Okay. Okay, so you do this branching, and after exhaustively doing this branching, what you will have is in this D, all the alpha k connected sets are not F free. So they are all F topological minor free. Okay, and then all these small connected components here that may not be F topological minor free, but the number of vertices here will be bounded by alpha k. If it is not bounded by alpha k, then again you can prove that our graph G is not unbreakable. Okay, it is breakable. Okay, that you can prove. So after exhaustively doing our branching, we look at all the small component and here in the bottom, their size will be at most alpha k. You guess where these vertices will go. Like some of the vertices will be should be placed in this elimination forest. You guess it. Okay, and then in the final step, what you do is you will solve vertex deletion for F topological minor free graphs on this large component with the parameter k prime being the k minus the number of filled vertices, k minus green. Okay. Now, once you find that, what you will do is you are going to place that vertices in some order here. That's it. Okay. So that will give you, that is going to give you an elimination forest for the graph. Okay. Now, why that is correct? Because we branched on all the connected sets of small size, which is not F topological minor free, and all the small components which is outside this part, which is going to have an F, which is going to have a graph from F as a topological minor, will allows us to say that there will be something which is this connected set which is F, not F topological minor free, and using that we can prove the reverse direction, and what we will get is, like, at the end we just do one execution of the vertex deletion problem, and if we are going to get an S answer, like whatever the vertex set deletion set we are going to get, we just place that in this field location, and that's going to give you elimination forest. Okay, so any questions you have? So we are going to find some small connected graphs, and we are going to branch, like if it is not F free, and after exhaustively doing that, we are going to do one invocation of the vertex deletion problem parameterized by the solution size, like the modulator, and then place it. Okay. So this leads to, so this is the algorithm, and I didn't explain how the reverse direction works, but mainly using, for the first one, it is maximality. For the second one, if we don't have these kind of things, then what, if there is a solution, any solution for this problem can be placed there. Okay. So assuming this is not possible, we'll prove that any vertex deletion to F topological minor free of size at most k prime can be placed here in this special route to leaf path, and then get a solution. Okay. So this proves, elimination distance to F topological minor free graphs parameterized by elimination distance is Fpt. And again, we have the third question. What about vertex deletion to F topological minor free graphs parameterized by elimination distance? How much time I have? I think I passed the time. So how much more time I can take?
A few more minutes, let's say 5 minutes, Fahad. Would that be?
Yeah, 5 minutes is good enough. Okay. So what we proved is, okay, now where did we use that, it is F topological minor free? Like, one is to solve this one, right? So if I have a problem, like if I have a, graph class H for which vertex deletion to H, parameterized by modulator is Fpt, then can we get an elimination distance? Not quite, because we also used the theorem by Loxanov et al. There it says that it should be CMSO expressible. So we could say that, okay, if my graph property has CMSO expressibility and it has, an algorithm for vertex deletion parameterized by the, deletion set size, then probably we will be able to, do the same. And there is actually a bit more things we need, which is to prove here, and that two conditions are, it should be a hereditary graph class and closed under disjoint union. What do I mean by closed under disjoint union? If I take two graphs G1 and G2 in H, then G1 disjoint union G2 should be in H. And what is hereditary? Every induced subgraph of, like, if G is in H, then every induced subgraph will also be in H. Okay, and these two properties we will use in this algorithm at the end to prove the reverse direction. Okay, like here, like at the end, like for our unbreakable case, these two properties, we need these two properties to prove the correctness of this one if H is some special graph classes. Okay, and so CMSO because of Loxanov et al, and hereditary and closed under disjoint union because we need that one to prove the correctness of our algorithm. And then so we will get a more general result, not necessarily just for F topological minor free graphs, but take any graph class H which is hereditary, CMSO expressible and closed under disjoint union, then vertex deletion to H is Fpt parameterized by and this condition, because we want to invoke at the end that deletion version of the problem, and then we will be able to get this one. Okay, and everything is same. I just took a candidate example being H equal to F topological minor free. Okay, the properties we use are these three. So you just substitute, these four. You just substitute these four and you can prove. Okay, by just verbatim going the same way. Okay, and then we had the following question, right? vertex deletion to H parameterized by elimination distance. Okay. Once we get an elimination forest, we can use that elimination forest to prove this theorem, vertex deletion to H parameterized by elimination distance. So intuitively, you can think that on tree width, if tree width is bounded or tree decomposition is given and your problem is CMSO expressible, then you will be able to get a good algorithm. And here we have CMSO expressibility and we have an elimination forest from which, like, these two together with some additional work, you can prove that vertex deletion to H parameterized by elimination distance is Fpt. Okay. And this gives us the following result, which means that let H be a hereditary graph class and CMSO expressible and this property hold, then all these problems are equivalent. Vertex deletion to H parameterized by modulator is Fpt, implies that elimination distance to H parameterized by elimination distance to H is Fpt, and this implies that vertex deletion to H parameterized by elimination distance to parameter is Fpt. And why this is this? I say this implies this. Why it is so? 3 implies 1. So we proved using 1, we proved 2. Using 2, we proved 3. Now, if it is equivalent, I want 3 implies 1 also. How do I get 3 implies 1? Any quick answer?
H is smaller than.
Correct. The parameter in 1 is more than the parameter in 3 because of that. Okay. So actually what we proved is in terms of Fpt, they are all equivalent. Now suppose what is the implication of this? Suppose you want to prove that vertex deletion to a particular a class of graphs is Fpt parameterized by elimination distance. You probably even don't need to know the definition of elimination distance. You need to prove, if you are able to prove that it has these properties, and design an Fpt algorithm for the plain deletion version of the problem parameterized by the solution size, you are going to get all of them. Okay. And H being hereditary graph class, CMSO expressible, closed under disjoint union, these properties is symbol properties, and for many graph classes this hold. For example, we have seen topological minor free, F free. So if H is chordal graph, it holds. If H is say interval graph, it holds. If H is bipartite graph, it holds. So if H is such that every connected component is either a planar graph or a bipartite graph, this property holds. Okay. So for a lot of various problems, you can say that you just need to prove, the plain vertex deletion version parameterized by, the deletion set for the modulator is Fpt. And that will give you, Fpt for all other kinds of parameterizations. Okay. So in that sense, it is a, a very strong result. Now, let me conclude. Okay. So all the algorithms I explained here, the main algorithms I explained, are non-uniform, not the algorithm on unbreakable graph, algorithm on general graph. And the unbreakability comes from, the CMSO thing, and applying the condition A. But we can get uniform Fpt algorithm when H is F free, F minor free, or F topological minor free, when all the graphs in F are connected. Okay, so that is a condition which I didn't mention yesterday for a question. So if all the graphs in F are connected, then we can get a uniform Fpt algorithm. Also, we can get a uniform Fpt algorithm when H is a chordal graph or bipartite graph or interval graph. This will not be subsumed by any of these F free, F minor free, or F topological minor free class. Okay. And fast algorithm, like now we can ask, like, what about running time? I just said FPT, and this running time is huge, like F of whatever that parameter is, that function F is huge. Okay. And also it is non-uniform, right? For many of here, there are uniform things, but still it is huge running time. Okay. What about, like single exponential or 2 to the polynomial in the parameter, like those kinds of running times for specific classes of graphs? That is an open question. And similar to elimination distance, which is a generalization of tree depth, Ibn et al. Like introduced the H tree width, which is a generalization of tree width. Our results extend to these parameters as well. And we get a result which says that, pretty much all deletion, elimination, H tree width version parameterized by any of the other parameters is FPT. Like all these are equivalent, like not FPT, they are all equivalent. You need to prove only one. Here only one is missing, which is, I think, elimination distance param by H tree width. This is missing. Okay, so this we don't know whether can be added to this one. That is also an open question, but this keep apart and all other versions, right? All the problems, like whatever, like, and with various cross parameterization, they are all equivalent. You can prove that they are all equivalent. So in terms of FPT, it is all same as, whether the plain vertex deletion version parameterized by solution size is FPT or not. Okay, that I will stop here. Any questions?
Thanks a lot, Fahad. Let me applaud on behalf of everyone. Yeah, so we have time for a quick question, I suppose. So Fahad, what is your belief about this missing case?
Which one? Sorry, I didn't get. No. Oh, I'm not able to listen to you. So others are able to.
We can hear you, Fahad. I think
I think MS sir was speaking.
Yeah, I think he asked, what is your belief about this last?
Oh, okay. Last belief is that will fit into this theorem. That will also be equivalent. Since all these are equivalent, which, yeah, it looks like it will also be equivalent. Any other questions? Okay, I think MSR's audio is not working.
Yeah, he sent the chat message saying thanks. And
okay, then bye. Thanks.
okay.